Hello, everybody. This is Kurt Munson from HBM nCode. Good morning, good afternoon, good evening to all of you out there in our global audience. Thanks for joining us in our continuing webinar series about nCode and fatigue and durability engineering. The topic today is, as you can see on the screen, applications of frequency-based fatigue analysis. I have to be very specific about what we're going to look at today. The key words, I should say, in this phrase are applications and frequency-based. So what I want to do today is talk about the concept of frequency domain fatigue analysis, the concept that is, not necessarily how to do this inside nCode design life, but rather to focus on the idea. When is it applicable? What are the strengths, what are the limitations, and so on. We've had other webinars in this series. As a matter of fact, just a month or two ago, we did a webinar on the specifics of how do we actually do frequency-based fatigue analysis, or vibration fatigue, some call it. How do we do that using nCode design life? So again, just to be very specific about what we're going to talk about today, today's focus is not on how do we actually do this in software, what button do I click on, and that kind of thing, but rather to focus on when is this a reasonable thing to do. Now, before we actually talk about the concept, I just want to make sure we're all on the same page here. So I'm just going to go take a look here. This is an nCode design life process that you may have seen previously. Maybe this is an analysis technique you use yourselves, or maybe it's something you've seen on other webinars here or something like that. The key is that this is how you actually go up and do fatigue analysis based on vibration stresses. So what I have here is a finite element model that I've solved for harmonic stresses. Down below, this is excitation in the frequency domain. I'm going to run this process here, let it run. I'm not going to get any details on how this actually works. The only reason I'm showing you this right now is just to remind you of what does vibration or frequency domain fatigue analysis look like inside nCode. In about a minute, we're going to finish looking at this screen, and we're not going to look at anything else related to software today. We're going to focus solely on what happened inside this process, when is it applicable, what are the advantages to it, what are its downfalls, what do we need to be aware of. So we're going to focus very much on the concept and the engineering of this process. Incidentally, while we're in here inside nCode, if you want to know more about how to build this process, I suggest you take a look in the lower left corner here on your manuals. There's a Design Life Worked Example PDF. A number of you guys I know have used this. This is a great way to learn about how to use nCode. The Design Life Worked Example PDF has 25 chapters, one of which is full of detail on how to build this exact process we see on the screen here. So like I said, we're not going to focus on how to do this or build this process from scratch inside nCode. If you want to know more about that, I suggest you take a look in the worked examples. Look at in the nCode.com archive webinars, or you can contact nCode support as well. I'm going to switch gears now and step out of design life now and think about the applicability of frequency domain fatigue. Let me just jump back here into PowerPoint. And let's think about what our agenda is today. We're going to start by looking at what is the frequency domain. Then we're going to transition to looking at what are the assumptions made in converting from the time domain into the frequency domain. Mathematically, or from an engineering perspective, what assumptions are being made when we work with this thing called the frequency domain, and what does that buy us, and what do we lose along the way? Item 3, we're going to look at what we call transient versus stationary time series data. And you'll see that this concept of transient versus stationary has a huge influence on whether vibration fatigue in the frequency domain is appropriate or not. Number 4, we're going to look at essentially what I was just talking about 3 there. When is this frequency domain appropriate? So when can we take advantage of the compact and fast calculation capabilities and such of working in the frequency domain? When can we actually do that and not lose our sanity as engineers by applying the wrong kind of technique to the wrong type of data? We want to make sure we're smart about this. We'll conclude by looking at item number 5, which is ways to represent vibration loading in the frequency domain. So you may have heard some of these terms, random or PSD loading, or sign dwell, or sign sweep loading, or sign on random, or Some of these are even more complicated these days, signed sweep on random. So I'll try to define what all these are and hopefully provide you with some background today that will help you understand when and where and how and why would anybody do fatigue calculations in the frequency domain. The reason why this webinar came to be honest, is we get a lot of questions. Since we have frequency domain fatigue capability inside Design Life, we get a lot of questions on the support hotline asking, okay, so what is this PSD thing? Where does that come from? Or I have time series data, what does that mean? Or I have impact loading. Can I represent that in the frequency domain somehow? Or someone told me that frequency domain fatigue calculations are the best thing ever. Is that really true? So I just want to try to flesh some of this out and give you some idea of when is this frequency domain approach useful, when is a time domain approach required instead, and how do the two different approaches compare and contrast. So let's look at this then. So I'm going to focus very much on people using finite element analysis for stress analysis today. So let's look at this concept of where does FEA and vibration and fatigue, where does it fit together? Okay, what do we have to know? So the idea is that a finite element analyst can use modeling in dynamic loading to understand fatigue life. So if you think about this as kind of a block diagram, FEA should tell us how loading becomes stress. And then loading can happen, which means that loading turning into stress becomes a stress history or a list of stress or fatigue cycles or something like that. And then from that we can calculate fatigue life. So that's the idea. We want to leverage the stresses we can get from FEA in order to extend our structural analysis past statics into fatigue. Since we're talking about dynamics today, we need to think about the dynamic version of this. So we're going to leave linear statics and that stuff behind us. We're going to think about the dynamic approach. The advantage to taking a dynamic approach to finite element-based fatigue analysis is that we can quickly assess design changes. So if this bracket were to change overnight, we can change the model, change the mesh, remesh, reanalyze, and recalculate fatigue life and see very quickly how does a change in radius or stamping technique or material, something like that, how does that influence fatigue life? Second point is that harmonic FE analysis is very computationally efficient. In other words, data in the time domain, if we were to look at running a direct transient in FEA, that could take an extremely long time. These days we try to limit the number of time steps if we're trying to run a direct transient analysis in the time domain. In the frequency domain, if we can represent the loading in the frequency domain, then harmonic or steady-state dynamics approach to stress in the FE solver can return results very, very quickly. And that's really leading into point number 3 here, which is we don't need to have long, bulky time series data to represent loading if we can represent that loading in the frequency domain. And that's one of the really fundamental questions today is, can we represent loading information, G loading or forces and moments, can we represent them in the frequency domain? The answer is yes, under some conditions. And we just need to talk about those conditions today. So what's the downside to this? Downside to using dynamic FEA and vibration fatigue analysis? Number one is that we have to be careful with mass and damping. So, stiffness and mass together will tell us what modes of vibration there are. Damping will tell us the magnitude of stress in those modes. And you'll find that damping assumptions are very important to understanding the magnitudes of stress. And as go magnitudes of stress, so go magnitudes of fatigue life. As a matter of fact, small changes in stress result in very large changes in fatigue life. So we have to be sensitive to the damping input here as being a very critical input into getting fidelity of our fatigue results. Second disadvantage is we have to be careful for nonlinearity. Obviously, if we're assuming something like a steady-state dynamics, then we're leaving out the transient part. We may be leaving out contact. We may be leaving out material nonlinearity, and so on. So we need to keep that in mind. And then lastly, this is really important. One disadvantage of this approach is that not all loading can be adequately represented in the frequency domain. And this is something we have to be aware of because vibration fatigue under inertial loading is a tool that we have to answer the question of how long will something break. But as with any tool, we need to understand its conditions. We need to understand its usage. Where does it fit? What's its domain? What use cases does it fit? So the question of
can loading be represented in the frequency domain is a very, very good question. It's a very frequently asked question, and that's a question we're going to answer today. So that's the idea. Now let's just think about what is this vibration. I keep using this term vibration, frequency domain, or inertial loading. So let's make sure we're all on the same page here. This is just off of a straight dictionary, some kind of like dictionary.com, I believe, what is vibration. The shame here is we have 5 definitions, 3 of which include the word vibrate. So there's a little bit of a circular reference here. The middle one, item 3, says something about physics. So as goes physics, so goes engineering. So I'm going to focus on that one. Vibration would just mean oscillating, an oscillating motion. So another way to think about this in an engineering perspective would be inertial loading. So vibration fatigue makes sense when we have parts that are inertially loaded. If we don't have that, we may have non-dynamic or quasi-static loads being applied, and those are not represented in the frequency domain nicely. So we have to keep in mind that vibration and inertial loading go together hand in hand. So speaking of vibration, if you speak with someone, say, in an NVH lab, or maybe your employer has a vibes group, they like to talk a lot about the time domain and the frequency domain. Now typically, measured loading data, how does someone actually use our part that we're building or designing? Measured loading data is typically measured in the time domain, and that's the squiggly line that's over on the left side here. This is G loading or moments, forces, whatever it is, something versus time. And we can learn a lot in the time domain. We can also transform that into the frequency domain, and that's seen on the right side here. Now the x-axis is frequency, and the y-axis something very much like the engineering unit seen in the time domain, but sometimes there's a subtle twist called the spectral density. And we'll figure out what that means in just a little bit. The point is we can look at measured time series data in the time domain. We can also use this thing called the Fourier Transform to convert it into the frequency domain. And we can also use a thing called an inverse Fourier Transform to work out of the frequency domain back into the time domain. So we're going to look at a lot of potential vibration data today in the time domain and in the frequency domain to help us better understand when can we take bulky time series data, maybe tens of thousands or even hundreds of millions of thousands of data points. When can we collapse it down to a nice compact frequency spectrum? When does that make sense in terms of the assumptions of the Fourier transform? And when does that meet our goal of being useful for engineering durability analysis? So we should talk about this Fourier transform. What does this Fourier transform actually mean? I have a lot of questions. People asking, what is this power spectral density thing, and what is the Fourier transform, and what does that actually mean, and how does it work? So let's just be very rigorous about how we define this. So the Fourier transform was Jean-Baptiste Fourier, a French mathematician's method of trying to take something in the time domain and think about it in terms of what we call sinusoidal basis functions. So there's a complicated equation down the lower left. If you like equations, then stare at that, and it may make some sense to you. You can also think about this graphically. A lot of people learn graphically, so I'm going to focus on the pictures on the right side. The measured time domain data is the squiggly line seen up at the top. And you may ask the question, is that a sine wave? And the answer is no. But Fourier would argue that it's actually a bunch of sine waves that we add together. And for those of you guys thinking about equations, add together, that's the sigma notation in the lower left. So what this means is actually a squiggly line, measured time series data up at the top, can actually be thought of as a bunch of different sine waves being added together. So the question is, though, what is the magnitude of each sine term? What is the frequency of each sine term? And what is the phase? So if we know frequency, phase, and amplitude of the constituent pieces in the frequency domain, we can build up the time domain. Just to look at that graphically, here's another example. Here's a square wave. The first question, is it periodic? Yes, it most definitely is. It has some characteristics that repeat over some time period. So yes, it is periodic. Now the question is that a sine wave? The answer to that, of course, is no. Sine waves don't have square edges. They have continuous or quite smooth derivatives, whereas sine wave has quite the opposite. So is this a sine wave? No. But Fourier, or those people who have been versed in the Fourier transform, would say we could actually think about the square wave as a bunch of different sine waves added together. We just have to think about how big are those sine waves. what frequencies does each one of them happen at, and what is their phase of one relative to the other. So graphically, we can actually think about this as that square wave is the summation, that's the sigma symbol again, the summation of a bunch of different sine waves. And you can see as we add more sine wave components, we start to get something that looks like a square wave, and we start to square up that edge. As a matter of fact, if we had an infinite number of sine terms, if we could do this over an infinite series, then we could actually make this square wave happen again. So what this means is we can map time series data out of the time domain into the frequency domain using the Fourier transform, and we can actually go backwards with the inverse Fourier transform and think about getting back into the time domain as well. This idea of looking at the same loading information in the time domain and the frequency domain is a lot like thinking about something else in your life in a couple of different ways. So for example, maybe I hide a treasure in the backyard and I want to give my kids a treasure hunt. So I say, okay, treasure is hidden in the backyards. How many different ways could I describe to them where that treasure is? One way would be, I could say, you need to go so many steps north and then go so many steps west. So, okay kids, treasure hunt, here's your map. Walk 100 steps north, 15 steps west, and then start digging. Find your treasure. I could also, if I wanted to test them a bit more, that relies on them understanding steps in north and west. If I wanted to test them in a different way, for example, test their ability to use a compass, I may say, orient yourself 8 degrees off of north, so slightly west of north, and walk 135 steps, or whatever the hypotenuse of that triangle is. So I can think about those instructions in two different ways, one being an XY kind of a basis, and the other being a direction, like magnitude and orientation kind of way. That's the exact same as looking at loading data in the frequency domain or in the time domain. We can learn things different ways. Both of them are just different representations of the same time series data. So this is Fourier's transform in action. That leads to this thing we call the fast Fourier transform. Fourier did this all on paper because he was doing his work in the late 1700s. The fast Fourier transform is the same algorithm, but optimized to work on a computer. And that leads to a thing these days that we call a power spectral density. And that's seen in this plot here. The x-axis is frequency again, so that's not too hard to figure. We're still in the frequency domain. The vertical axis, though, is in g squared per hertz, which may sound really weird because we started with g's, and then we converted into g squared per hertz. So in the time domain, we have g's. In the frequency domain, now we have g squared per hertz. Why is that? It's because once upon a time, electronics engineers, actually almost 80 years ago, electronics engineers didn't have a computer to calculate noise in their electrical circuits. So instead, they built up a little calculating engine using resistors and capacitors and whatnot to measure the power being transmitted through these electrical lines at different frequencies. So as a result, their analysis, their analog calculator, created this thing called the power spectral density, which has these weird units of g's squared per hertz. Now these days, with a calculator or a computer, we can use the fast Fourier transform. We can actually calculate an amplitude spectrum in g's versus frequency instead of a power spectral density in g squared per hertz. It'll tell us about the same information. It's just the vertical axis will be scaled into g squared per hertz or in g's. Same type of idea. So we can look at this in g's versus frequency if you want, or in the traditional g squared per hertz PSD form if you want. The PSD form sticks around today just because it was so prevalent over so many decades of engineering that it has a lot of inertia of its own going forward. A couple points to make here. The square root of the area under this curve is the RMS of the time series data. So one measure of activity or what would you say, like one level of G loading energy is what we call RMS, the root mean square. We can calculate that in the time domain, and we can also calculate that in the frequency domain as the square root of the area under the PSD curve. So we can learn a lot by looking at things in the frequency domain. We can learn a lot by looking at things in the time domain. One point to make is that these amplitudes that are seen in this plot here, these amplitudes represent, say for example at 40 hertz, there's kind of a peak there at 40 or 45 hertz. that represents the average amplitude of a 40 hertz sine wave running through the time series data. So the key point here represents an average amplitude or average power running through the time series. So average, that's the key word here. It's going to come back and make us think a little bit about the loading data and should we be representing it with averages or not. So let's investigate that right now. So let's look at this idea of what we call stationary versus transient time series data. When we calculate a PSD, or an amplitude spectrum, we assume that the time series data is stationary. What I mean by stationary is that the characteristics of that time series data are not changing with time. So this is data measured in the time domain. This is a pretty random looking signal, but kind of stationary versus time. Stationary meaning that we hit the same peaks pretty repetitively. There's not a lot of difference. If I were to grab, say, a 1 second long chunk of data somewhere in here and look at its statistics, and then like max and min and RMS and those kind of statistics, if I were to go grab another chunk of data, say a second long, just randomly, another second, and calculate the statistics, they'd be quite similar. In other words, there's not things that are really changing. The loading information is pretty consistent second after second after second. In other words, that means if the PSD is showing us the average amplitude over time, the amplitude has a pretty consistent average over time in the time domain. So therefore, I have a better feeling about the amplitudes that are being returned in the PSD. In other words, the PSD has a pretty reasonable understanding of the statistical averaging, through statistical averaging, that are represented in this process. Now, the converse to the stationary time series data is what we call transient. So you can see in this time series data that there are some big peaks that are not periodic or repeating. There's some times in which very large peaks occur. There are some times in which very small magnitudes are seen. And there's some times where we see other things that look completely different. This is very typical of, say, chassis loading over, say, curb strikes, or say an offshore oil platform that gets hit by a huge transient wave. Some wave loading may be quite predictable and follow kind of a distribution of peak wave heights. But if there's the rogue wave that slams into the oil structure at some point, that causes some kind of a transient response. So the question here is, if we have transient data like this, how well can we represent those transient peaks in the frequency domain? Remember, the Fourier Transform is going to look at an average amplitude. It's kind of like fitting a sine wave of a given frequency into the time series data and returning what is the average amplitude of that sine term in Fourier's sum. So clearly, looking at averages, what's the average loading look like with a transient signal is a bad thing, because averaging out peaks is going to reduce peak stresses. That's going to influence our fatigue calculation. So that raises the question, what's stationary, what's not, and how does that influence our calculation? So let's look at it this way. There are some tests, if we have to be aware that transient peaks are lost when doing the Fourier Transform, that raises the question of maybe we should have an idea of whether the time series data is stationary or transient to begin with. There are a number of ways to look at this. Some statistical approaches are available inside nCode to look at things like peak loading. There's a statistical thing called the crest factor, which says what's the RMS of the time series compared to the peak of the time series. So how many peaks tall is the RMS? That's one way to look at how peaky or how transient the time series data is. There's also going to be shortly in nCode 11.1 or 12, one of our future releases, there will be a new glyph for looking at testing stationary versus transient time series characteristics. What I've done here in this particular plot is I've taken some time series data. I'm going to calculate its FFT, and then I'm going to do the opposite of that, invert that FFT back into the time domain to look and see, do the assumptions of stationary behavior that are inherent in the FFT, are they reasonable or not for this time series data? So what happens here is I've measured time series data at the top, I calculate its FFT, I don't even look at the FFT here, but I then give the FFT results to the inverse FFT to work back into the time domain. Now, working back into the time domain is not a deterministic or unique transform. In other words, from amplitude and frequency, or power and frequency from the PSD, we can't get back to the time series we started with. We get back to a time series that's representative of the frequencies and amplitudes or powers in the frequency spectrum. You can see here, if we have data that's stationary or truly random looking in the time domain to begin with, then working into the frequency domain is a reasonable thing, that the application of stationary assumptions in the FFT are reasonable, because if we invert that result, the inverse FFT, the time series data we get back out of that, looks a lot like the measured data we started with. You can see the peaks here, roughly plus or minus 4 Gs. So since we had random stationary data to begin with, the FFT truly captures that information and would be useful then for our vibration fatigue calculation. Therefore, we call this inertially approved or vibration approved. Let's look at another use case. This is some time series data. You can just kind of eyeball in the time domain that it's a little bit less stationary, or a little bit more transient, a little bit more characteristics are changing over time just by looking in the time domain here. You can see there's sometimes when the amplitudes are not large and sometimes when amplitudes are large. So let's apply this concept of stationarity through the FFT and then invert back into the time domain, and we get something that looks like this. Now, I've violated one rule of comparing time series data, and that is I've got different axes on these two plots. The top one goes plus or minus about 500 or 600. The bottom one goes plus or minus 400 or 500. So I really should plot these on the same axes. But what I'm trying to show here is that by taking the time series data and applying the FFT to it, we assume that the peaks are stationary, or we're looking at average magnitudes of peaks throughout the time domain and representing those now in the frequency domain, which means if we were to work backwards and invert back into the time domain, now we do have truly stationary data, but the peaks aren't as big, right? Peaks aren't as big. That's the start of a problem here, because as go peaks, so will go stresses. As go stresses, so will go fatigue life. So we have to be a little bit careful here. As our time series data has transient peaks in it, we'll start to lose that information in using this vibration fatigue calculation. So this raises a question, is this good enough? Here's the worst case scenario. Here's really peaky transient time series data. So the question at the top of the slide, is this stationary? I think if you've been paying attention here, you should think to yourself, or maybe even say out loud to your cube mate, that is not stationary time series data, that's transient, okay? What happens if we take transient time series data, run it through the frequency spectrum calculation, back into the time domain? We lose all the peaks. So again, the y-axes are a little bit different here. But if you look carefully, you'll see that we lose all the transient peaks by applying Fourier's math. Now, some of you may say, hey, wait a minute. Actually, in the fast Fourier transform, we have an option. We can have the frequency spectrum y-axis be scaled as an average amplitude or as a peak amplitude. Okay, so we can look at an average or peak amplitude. I've said average a lot today. True, peak does exist. A peak amplitude would say that we'd pick up peaks that way, but that would say in the frequency domain that peaks always happen, right? So our two choices, we kind of have two box ends in our frequency spectrum, either what's the average amplitude or what's the worst case amplitude. And very rarely with transient data is it true that the transient stuff keeps happening with the exact same peak amplitudes. And also with transient data, we can't also say that the average amplitude makes sense. So this is where things start to fall apart. When we have transient data, this concept of understanding data in the frequency domain starts to become tenuous. So in this case, I would say this is not a good thing, denied. So why does this matter to fatigue? Well, step by step here. If we take time series data and convert it into frequency domain, that implies that the time series data was stationary. If the data was not stationary to begin with, that means we lose transient peak data. If we lose transient peaks, then that means then we lose stresses. And if we lose a little bit of stress, we drastically change our fatigue calculation, because stress is an exponential input into fatigue life. So fatigue life is an exponential function, power function, exponent not equal to 1, in our fatigue calculation. So what that means is, if we have transient peaks like you see in the data on the left, keep in mind that if we choose to represent it in the frequency domain, we're essentially saying that all the peaks are the biggest ever, or all the peaks are the average, which is seen on the right side here. So we have to be careful relying on the frequency domain to describe all of our fatigue loading. The closer we have to stationary data, to purely inertial loading without transient shock, that kind of thing, the better off this vibration and frequency domain fatigue calculation will work. The closer we are to peaks and curb strikes and transient behavior and such, the worse our vibration domain fatigue calculation will work, in which case we could look at something in the time domain, which of course nCode has a series of tools for as well. All right, so I just said we could look at things in the time domain, we could look at things in the frequency domain. Just a quick comparison of the two. If we had infinite compute resources, we could do everything in the time domain. We could use a direct transient FEA. Or maybe if we didn't have infinite resources, but you know, a good kind of compromise here would be use a modal transient. So both time domain approaches, either direct or modal. The beauty of these two things is that it's easy to visualize things in the time domain. We can keep those transient peaks, and also we can understand the relationship between multiple channels. So in other words, if we have multiple degrees of freedom of loading, say 3 forces, 3 moments, if we're not careful in the frequency domain, we can lose the phasing information when one has big peaks. Say when fx is large, what's fy, mx, mz, and so on, what are those doing? If we do work in the time domain, we can keep track of that information very easily. The downside, of course, to working in the time domain is that we have a long calculation time. We have very large data files in the time domain. Typical loading information can span tens of thousands, even millions of data points to describe them in the time domain. And of course, compute resource becomes a huge headache at that point, which leads us to the frequency domain concept, looking at harmonic stresses, steady state dynamics. The beauty is we can capture dynamics this way. The calculations are quick, but we have to keep in mind that we lose time duration, and also we lose transient behavior. As we have seen before, some time series data has transients in it. Those transients drive large stress cycles. We need to keep track of those. So another way to look at this question of should we use time domain or frequency domain is to look at a plot like this, kind of a roadmap here. Let's try to answer the question of how does this part behave when it's loaded. So let's start with a part, and if it's loaded in some way, what will the response to that loading look like? Quasi-static loading, awesome. Let's use something static. We could use nonlinear statics, we could use linear statics, lots of stiff, chunky parts, or parts that engage the ground like a loader arm, or like a bridge structure, that kind of thing. Lots of things behave statically. And if that's the case, then we don't have to think about any of this dynamics we've been talking about today. But I know for a fact lots of things vibrate out there, flagpoles and parts on rocket ships and parts on cars and even parts on bikes and radio components and all kinds of electronics and so on. So we need to think about dynamics. We have dynamic loading. The next question is the loading transient or is the loading steady state? And we've used the word transient a lot today. We've used the word steady state, or instead of steady state, you could use the term stationary. If it's transient, then we really ought to be working in the time domain, solving with a direct transient, or we could use a modal transient as well. So remember, transient peaks, we want to keep track of them in the time domain. If we have steady state loading that's not peaky, that's stationary, then we can start to think about doing things in the frequency domain, and we can look at then different types of loading, like we used some of these words before, the random PSD and the sign dwell and the sign sweep and so on. And I'll try to define what some of these mean in coming slides. Here's some examples of things that vibrate out there in typical frequencies of interest. So wave loading on ships and oil platforms and other marine structures tend to be quite low frequency. As a matter of fact, sometimes the frequencies are low that these numbers get to be little teeny decimals. So often they talk about wave number or cycles per second or cycles per minute instead of hertz, which is, excuse me, they refer to seconds per cycle or minutes per cycle at very low frequencies, because that might be easier than saying frequency of 0.05 or 1/20th of a cycle per second. Wind turbulence, earthquake loading, things in cars, aircraft, helicopters, trains, all kinds of different frequencies here. This table is really just here as a reference for you to think about things you're working on. What are the frequencies it can vibrate in, and what frequencies are the loading that are applied to it, and frequencies of vibration, so modal characteristics, and frequencies of applied loading, of course, will come together to cause resonance, will cause stresses, will cause fatigue damage. The last column on the right is loading type, PSD, time domain, swept sign, PSD. So I need to talk a little bit here yet. We've defined time domain and PSD, but we haven't looked at swept sign or sign on random. So we'll look at those cases in just a minute. A lot of times parts are tested as part of their development process or validation process. They're tested on a shaker rig. This is an LDS electrodynamic shaker rig, and the idea here is that this is essentially a big speaker working upside down. The beauty of speakers is that we can listen to music through them, and the way that works is excitation to the coil and the magnet causes the speaker itself to vibrate, and as it vibrates, it moves the air, and then we hear things, and we get up and sing along or dance, whatever it is. But anyway, this essentially is the same idea. An electrodynamic shaker like this is controlled in such a way that it will move the crosshead or the platform up at the top that will have the device on test bolted to it. It'll shake that. It'll move up and down just like a speaker would move up and down to cause vibration and cause sound. This is shaking up and down at different frequencies and different amplitudes to cause vibration cycles. So this could be what we call random or PSD loading, which means we have a PSD of so G squared per hertz as a function of frequency, all those sine tones or frequencies and amplitudes being played out at the same time. So this sounds like a steady kind of a or something like that. It can, like maybe an engine running, but not changing its speed, right? That's the random PSD case. The harmonic case, that could be a sine dwell or sine sweep. Sine dwell is no need to run lots of frequencies if we have only one resonant condition we're trying to excite. So a sine dwell is run just one frequency instead of all those PSD frequencies randomly phased together. Sine sweep would be like replicating an engine or something with rotating componentry, where the sine tone happens because of something, say, rotating or in imbalance or firing or something like that. But then its frequency will sweep up and down, just like the jet engine's speed will sweep up and down through usage as well. And then these days, a lot of people talk about a mixture of these things, a random plus harmonic. So a sine on random or a sine sweep on random. And we'll look at the idea of sine sweep on random and sine on random in just a little bit. So this is the shaker rig that may be in your test lab that is used to create inertial stresses in a part as part of a validation test. And the beauty of design life is that we can replicate this through the process I showed you at the very start of this presentation. We could call that process the virtual shaker table test, because we can have FEA plus design life together working to understand dynamic stresses and understanding how those influence fatigue life. One thing to keep in mind about these shaker rigs is that frequently these shaker rigs can only excite only one axis at a time. So in other words, we may have PSD loading in the X, Y, and Z directions. That's seen on the left side here. But often these shakers are limited to only being able to shake one axis at a time. In other words, we shake X in the we shake in one orientation with X vibration PSD levels that you see. And then we turn the part 90 degrees and we give it a shake with maybe a different frequency spectrum, different PSD loading in the Y direction, and then following the Z direction. That's typically one, you could say, boundary condition or constraint of a test rig like this, is that it's often capable of only shaking one direction at a time. So we run typically 3 axes in sequence, not simultaneously. But you think about it, we actually have in the real world this car or the jet engine or the electronics, the iPhone in your pocket, or your iPhone that's been shipped overseas to end up at your local mall for you to go plunk your money down on. Any real-world vibration scenario probably has multiple axes of vibration at the same time. So if our goal is then to be able to predict fatigue life, we may want to replicate the test rig at the top with multiple axes in sequence, or we may want to replicate the real world, which is multiple axes acting simultaneously. Now, we can do either one of these calculations inside Design Life. As a matter of fact, we did a webinar just recently on how to do this inside Design Life. We've done the uniaxial case, or the multi-axial in sequence case for a long time now, and just recently in nCode 11, we added the multi-axis simultaneous case, where we need 3 PSDs and also what we call the cross spectrum that tells us the phasing of how excitation in X, Y, and Z all work relative to each other. So if you want more information about how to actually do this, to build this Design Life process, please look at the Design Life work examples or contact nCode support or look on the ncode.com archive webinars for more information about that. So let's talk about how do we actually, behind the scenes, what's actually happening with a random vibration fatigue analysis. So random vibration, you know, again, this makes sense when we have stationary time series data. This is wind gusting or turbulence on the aircraft, or vibration loading from an engine or from a large mechanical device that rotates. This random vibration case, you know, the wind gusting takes on kind of random characteristics. If we collect data over a very long time period, we may find that we can start to get an average peak levels and things like that. And it may be easiest, honest, to take that long time series data and think about it in the PSD form. And that's what's shown down at the bottom of the page. The time series record may be very, very long, tens of millions of data points, whereas the PSD representation of that, if it makes sense, if the time series data were stationary, the PSD representation is very compact. It may be even just a couple hundred data points, hundreds instead of millions of data points, which can have huge computational efficiencies for us when we come to do fatigue. Now, cycle counting a PSD is always, or any random vibration process, is always an interesting concept. If you've been around fatigue before, you probably recognize that one of the key steps in a fatigue analysis is understanding how many cycles happened and how big were those cycles. So how many cycles of what size is a critical input to any fatigue calculation. That's typically done with a technique called rain flow cycle counting, which is trivial to do in the time domain, but a little bit more complicated to do if we're working with frequency domain stresses. Now keep in mind, the reason why we're talking about frequency domain here is, again, that if we do everything in the frequency domain with steady state dynamics or harmonic stress solution in FEA, the beauty of that is the stress results are very compact. We end up with what we call a stress PSD, and that stress PSD needs to be cycle counted in some way. So we end up looking at a statistical approach to cycle counting. So it's a statistical cycle counting approach as opposed to a deterministic approach that we use in the time domain. Why statistical? Well, think about it this way. If you were to look at, say, the wind blowing and causing stress cycles on a road sign, if you were to go out and collect wind blowing data over a very short time period and then look at how many fatigue cycles happened of what size, we might end up with a plot that we see in red here. So the vertical axis is the number of fatigue cycles, and the x-axis is how big were those fatigue cycles. So with 10 seconds of data, we probably don't have a very good statistical understanding of this random wind blowing process. As a matter of fact, if we were to collect data for a longer time period, we might find that the statistical distribution of cycles takes on some additional or interesting characteristics. That's what's shown in the blue here. Notice that two things happen. The longer we collect the data, the smoother the distribution of cycles is, and also the greater probability there is of us finding a bigger peak. Right? So if we collect data over a longer time period, we start to understand better the distribution of the small and intermediate peaks, and also we have a better chance of capturing a big gust of wind. As a matter of fact, if we collected data over an even longer time period, we might get this green cycle count, which is, again, saying a better distribution and also a better understanding of the tail of the population. The tail here on the right side is important because in fatigue, it's typically big cycles that dominate fatigue. The things that damage the most are the big stress cycles. So our ability to understand statistically the big cycles that happen under random loading is critical to fatigue. And really, so the cycle counting approaches all come down to what statistical distribution best fits measured data of random phenomena. We can't afford to go out and measure random phenomena like wind gusts for days and days on end. Or, I mean, honestly, we should probably collect, if that was really truly random gusting, we should probably collect over a whole year or a series of years to understand differences in wind gusting in the winter versus the summer and such. We don't want to do that. Even if we did, if we had wind gusting in the time domain for several years on end, would you want to run a direct transient in FEA with that? The answer is obviously no. So our best approach going forward is to use the frequency domain, but understand what's the best statistical distribution to represent that random phenomena of wind gusting. So all this frequency domain fatigue stuff is based on statistical cycle counting techniques. And that's what this black dotted line is showing us here. If we had a harmonic vibration, so for example an engine turning over, we don't have to worry about statistics and random vibration and such because we have something that's quite periodic that's happening. You know, for example, if we just look at, take the engine and let's say we're turning it by hand. So let's say it's on a dyno and there's no gas, no combustion inside of it. It's going to rotate, and probably because of imbalance or valves closing or something like that, we'll get stress cycles that happen once per revolution, maybe twice per revolution, something like that. And it's relatively easy then in this what we call harmonic case. It's relatively easy for us to understand fatigue cycles, right? Because we can just look at every revolution, there's a first order cycle, twice per revolution, there's a second order cycle, and so on. So there's no randomness involved. This is the harmonic case. Sometimes this harmonic case is described as a sign dwell loading or as a swept sign kind of loading case. So there's not randomness we have to worry about here, but we still have to understand the dynamics of how do stresses arise at different frequencies under this harmonic loading case. Now imagine if you have a helicopter or the engine that was on the previous slide, and this time in the engine you filled it with gas and actually ran it. So it had bang, 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 bang explosions that are transients, right, that were causing things on top of the rotation. Or in the case of the helicopter, we may have harmonic and random parts. For example, the harmonic bit of a helicopter is every time a blade passes over the structure, over the tail, we're going to have a whoop, 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 whoop. We get one of those whoops from the downdraft of the blade passing over the top of the helicopter. So the helicopter will have random stuff going on because it's got an engine, it's got wind loading, turbulence maneuvers, all that kind of stuff. It sees random loading. And also it has the whoop, 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 whoop kind of characteristic from what we call blade pass vibration. So often this kind of thing, an engine running with randomness because of combustion, with harmonics because of rotation, a helicopter with harmonics from blade rotation, and randomness from turbulence and downdraft and such. We often represent this loading with what we call sign-on random loading, or sometimes even more complicated than that, swept sign-on random. Sign-on random would be like we have a sine tone that happens at a fixed frequency, and then we have randomness on top of that. That would be like the helicopter running at a fixed blade RPM, fixed rotor RPM. Swept sign would be the same thing, but with the rotor changing frequencies over time. So this leads to the case of the sign-on random or swept sign-on random loading. Now the beauty of this is that all these different types of loading we can account for inside design life. So if you can calculate stress in dynamics in FEA, and if the loading data can be collapsed down into the frequency domain representation like a sign dwell, random, sign-on random, or swept sign-on random, then design life can take all that information in and do a reasonable job at a fatigue calculation while enjoying the benefits of working in the frequency domain. So this still raises the question, though. A lot of people ask, this whole swept sign versus PSD, what does that really mean? It doesn't matter. I've had several people ask me over the years, does it? I have this excitation to apply. Does it matter if I call it random PSD or swept sign? And the answer is yes, absolutely. In physical sense, it matters. If you're running a test with random versus sweeping excitation, the stresses that would arise in the part would be quite different. If you're doing a fatigue analysis inside design life, then yes, absolutely, the stresses will vary depending on whether we have random or sweeping excitation. Just remember, random PSD says that we have all these frequencies of excitation. All these frequencies of excitation all happening at the same time. Whereas a sign sweep says we have all these frequencies of excitation, but they happen in sequence. This is the same as looking at sheet music. So a sign sweep is like playing scales, a progression of notes, whereas a PSD is playing all those notes at the same time, and that's what you call a chord, right? So if you were to play a sign sweep on the piano really loud, or a chord really loud on your piano, which do you think would hurt your ears more? Which would make a louder sound? Clearly it's playing all the notes at the same time because their sound energy is combining to make an even higher sound level to your ears, so you're damaging your ears faster. Same thing happens with vibration and inertial stresses as well. Typically, sign sweep loading doesn't produce really high peak stress cycles because we're playing out these excitations in sequence, whereas random PSD tends to be more damaging per unit time because the excitation is creating stresses that are then superimposed on top of each other and create higher peaks, therefore create more fatigue damage per unit time. All right, so let's wrap this up. What is going on here? What's the concept? Well, we have some advantages if we can take a frequency domain approach to fatigue, but the question still remains, is that applicable to your data or not? So, what are the advantages of using frequency domain fatigue? We don't need lengthy time series data. So, if you've gone through this calculation before, measured loading can be extremely long in the time domain and may be prohibitively long, so we'll never be able to use it as, say, a direct transient in FEA. So if we can get away from the time domain and look at compact frequency spectra and such in the frequency domain, then we save a lot of time series data. That also means it'll compute faster. So both the FEA and the fatigue solution will speed up drastically if we can properly represent the time series loading data in the frequency domain rather than the time domain. Another nice thing is here we weren't accounting for dynamics and resonance. So if your model, if your FE model is masked up appropriately, and if you can understand the role of damping in that, then we'll be able to understand dynamic response and resonance and such, which is great, because now as an engineer, you can check the box that says, okay, your fatigue analysis, sir, did it account for resonance or not? Because I think resonance is going to be a problem. So this way we can account for resonance. And then lastly, we can look at the statistical side of loading, because remember we looked at this a couple plots before of, say, wind gust loading. The longer, if we could have sampled data the longer and longer in the time domain, we'd get a better statistical understanding of how often the big gusts happen versus how often the small gusts happen. PSD loading and PSD cycle counting techniques can inherently have that statistical variation built into them. And this is a great thing because now, in a compact way, the PSD can represent loading, and the rainflow cycle counting, a stress PSD, can account for statistical variability. Now, this all sounds very good. There's some great reasons to use vibration fatigue, but just keep in mind, on downsides, we also have to keep in mind that in converting from the time domain to the frequency, we lose transient magnitudes. So we're looking at either peak amplitudes in the frequency domain or average amplitudes in the frequency domain. The problem with average amplitudes means that then we're losing bigger loading cycles and we're losing bigger stress cycles as a result. The problem with using the peak loading information, if we chose to calculate what we call a peak hold PSD, that's a reasonable thing, but it's hard to use in fatigue because that then says that every cycle that ever happened was however big the biggest cycle ever was. So in other words, that would mean that if I were to, say, look at peak wind gusts, if I were to look at wind gusts over a long time period and look at the average, well, that's not quite as big as some of the cycles were. If I look at the peak hold, that says that we always had the worst case wind gusts constantly. So we're stuck in this kind of no engineer's land between one assumption of this assumption of stationary with averaging results in stress cycles that are too small, and with peak hold that results in stress cycles that are worst case and too big. So that can be a real challenge. So just keep in mind that if you have transient or impact loading in your actual loading data that you're trying to apply to this part, keep in mind that we're going to wash out transients in going into the frequency domain. So with transients, you'll want to stick with the time domain. And to be honest, one of the beauties of this approach is that we could actually analyze some loading scenarios in the time domain and some in the frequency domain. I've seen a number of people do this with success, looking at the transient stuff using transient or modal transients, direct transients or modal transients in the time domain, and then looking at the fatigue damage contribution from the other more stationary loading histories using vibration fatigue. So that concludes what I had planned to talk about today with vibration fatigue and the concept thereof and where does it fit